Similarly, I want to get the phase plot. For the phase plot, write the phase angle expression. Now, in this particular problem, we have two zeros in the numerator and two finite poles in the denominator. So, two zeros directly I will get plus 180. So, phi is equal to plus 180 minus tan inverse 0.1 omega minus tan inverse 0.02 omega. So, this is the transfer function phase angle expression for the given transfer function. Now, again I can prepare a table. In this table I have first column is omega values which is varying from 0 to infinity, then here are corresponding phase angle values. So, first of all we will take at omega is 0, what will be the phase angle? When omega is 0, the phase angle is going to be plus 180 degrees because we have minus 90 p naught minus z naught. So, minus 90 0 minus 2, that is going to be plus 180 degrees. So, the graph will start from the plus 180 degrees. In semi-log graph sheet we cannot get 0, omega is 0, but we can have some idea that from where this graph is coming. So, the graph is coming from plus 180 degrees. So, when omega is infinity, it is going to be 0 because minus 90 p minus z, there are two poles and two zeros, therefore it is going to be 0. So, when omega is infinity, finally it is going to be 0. So, in between we need to take omega values and find out what are the corresponding phase angles. So, some of the typical values you can choose. When it is 0.1, then it is going to be around plus 179. So, when it is 5, it is going around 130 nearby. When it is 20, then it is going to be 83, and like that when it is 100 and it is 30. So, we have values like this. So, plus 180 to 0 it is going. So, using these points, then I can locate and I can draw a smooth curve which is the phase plot. Let us look at the semi-log graph sheet, and we know the frequency ranges. We have 0.1 to 50, 100. So, that frequency range we can assume. Let us the leftmost one is 10 power minus 1, that is 0.1. Next is 10 power 0, 10 power 1, like so. We can take the frequencies. Then MdB values for each unit I can take it as a 20 dB, and I can list down all those things because it is varying from minus 48 to we have plus 48. So, all these values we have to choose it. So, next for phase angles, you can take the right side angles. So, each unit I can take it as a 30 degrees, and I can have the scale in the right side. Left side I have MdB values, right side I can have the phase values, and x axis all omega values. Now, so when you locate the points of the magnitude plot, we have at 0.1 minus 40 dB for minus 40 dB, and when it is 5 and we have it is 28 dB, and when it is 50, then it is going to be 48 dB, then again for 100 also we have 48. So, it is from minus 40 to 28 increasing because we have two zeros in the numerator in this transfer function. Therefore, because of that the initial slope is plus 40. Plus 40 means it is increasing. So, we have, that is why we have increasing here. Then after that it is 20 dB for decade, then after that is 0 dB for decade. Then I can write here this is plus 40 dB for decade, plus 20 dB for decade, 0 dB for decade. So, this is a magnitude plot. Next we can plot the phase plot also. So, the phase plot is I am taking from 180 degrees to 0, and so I can look at all the points. So, when you look at all the points, then the smooth curve is going to like this. So, how it is changing from plus 180 to 0 for all the points, what are the points we calculated after locating. Now, so once the complete magnitude and phase plots are available, then it is time to get what are the phase crossover frequencies and gain crossover frequencies. Now, look at what is the gain crossover frequency, the frequency at which the magnitude is going to be 0 dB. So, the magnitude is 0 dB. When you look at this graph, exactly at 1 radian per second it is crossing the 0 dB. So, I can say omega gc is 1 when k is equal to 1. In the problem initially we assumed k is 1. So, omega gc is 1. So, at omega gc then I can drop down to the phase angle, and we can find out what is the corresponding phi gc. The phi gc is going to be minus 162, then the phase margin is going to be plus 18 degrees. So, phi gc, omega gc to phi gc to phase margin I am getting it as plus 18 degrees. Similarly, omega PC, what is omega PC? It is the frequency at which the phase plot crosses or intersects the minus 180 degrees. But in this case, the entire plot is within plus 180 and 0. There is no minus 180 at all. So it is not at all crossing minus 180 degrees. I can take omega PC is infinity, the corresponding gain margin also infinity. Therefore, when K is 1 in this particular system, the system is stable. Closed loop system is going to be stable because gain margin is infinity, phase margin is a positive value at plus 18 degrees. So next step is then how to find the K value for given gain crossover frequency. What is a gain crossover frequency? It is the frequency at which the magnitude plot intersects the 0 dB line, cross the 0 dB line. So when K is 1, it is crossing at omega is 1 radian per second. Now the required K value at omega GC to be 5 radian per second. Now look at 5 radian per second, what will be the MdB value? So for 5 radian second, the MdB value is 28 dB. Now what I want to make the 28 dB to 0 dB, which means I need to shift this magnitude plot downward direction so that the 28 dB becomes 0 dB. Now that in this case, then omega GC is 5 radian per second. So since we are shifting the magnitude plot downward direction, then I can equate the expression as 20 log K is equal to minus 28 dB, because how much amount of dB we are shifting down? 28 dB. Therefore 20 log K is equal to minus 28 dB. We can find the K value, it is around 0.039. So since we are shifting down, the K value decreases. Initially K value is 1, now it decreases to 0.039. So in this particular system, if we choose the gain value as 0.039, then we can obtain the gain crossover frequency as 5 radian per second. Let us look at how to draw the Bode diagram for time delay systems. So let us take one example of system with time delay g of s directly e power minus std. So this is the term which is responsible for time delay. For this term, let us see what will be the magnitude expression, what will be the phase angle expression. Now, so g of s is equal to e power minus std, but td is a delay time. So we already know delay time, if introduced in the system behavior completely changes. Sometimes even the stable system may become unstable system, or the performance of the system which is already very good, when you introduce more delay into the system, the performance may be degraded. So that is the delay time td. Now, so substitute s is equal j omega. When you substitute s is equal j omega, g of j omega is equal to e power minus j omega td. So e power minus exponential term, e power minus j omega td. What will be the magnitude of it? The magnitude of it is going to be 1, because whenever you e power term, that can be written in sine term and cos term. Then when you take the magnitude of that, then it is going to be 1. So magnitude of any time delay term will be unity. What will be the phase angle? The phase angle is going to be minus omega td. So this will come in radians, but phase angle should be in degrees, therefore 180 by pi. So the phase angle contribution of time delay is going to be minus omega td into 180 by pi. Now, so let us take one simple example and see what will be the effect of the time delay. Let us say my open loop transfer function gh of s is e power minus 20s divided by s into s plus 2 into s plus 4. So without going into complete details of the problem, I can say that this particular system is going to be unstable with the time delay 20 seconds. So when time delay is 20 seconds, it is unstable. But when you change the time delay from 20 seconds to 2 seconds, which means when gh of is e power minus 2s divided by s into s plus 2 into s plus 4, so this system is going to be stable. So certain values of time delay system is unstable, and other values of time delay system is going to be stable. Then what will be the critical value of that? What will be the critical value so that I can have the complete differentiation from stable to unstable. So the critical value of time delay, we have formula, that is TDC. Critical value of time delay is PM naught into pi by 180. So this PM naught is the phase margin when TD is equal to 0. So what I can do is initially assume the time delay is 0, then get what is the phase margin, maybe using analytical method or graphical method. So that into pi by 180 gives the critical value of time delay. With that critical value, then system will be at marginally stable. So for the example which you have taken, the critical value is going to be 12. That means when gh of s e power minus 12s by s into s plus 2 into s plus 4, the system will be marginally stable. If TD is greater than that, the system will be unstable. TD is less than that, system will be stable.